Welcome, everybody, and thank you so much for coming at this unusual hour. And we very much thank Masato for coming, who is talking to us from Brisbane, and it is 11 p.m. at night there. So warm welcome, and thank you for coming. It is my pleasure to introduce Masato Yamamichi, and he's going to be talking to us about rapid evolution and coexistence. Please mute your microphones for the durations of the talk, and without further ado, Masato, please, the floor is yours.
Thank you. Thank you for inviting me. I'm a night owl person, so I'm really looking for this presentation. So today I will talk about the effects of rapid evolution on species coexistence and two studies on this topic. Okay, so I will start from the short background on the relationship between the rapid evolution and species coexistence. And then I will talk about how intraspecific adaptation load can promote coexistence. And then I will show you how rapid evolution can promote the fluctuation-dependent coexistence. And finally, I will shortly discuss the potential synthesis of eco-evolutionary dynamics and species coexistence theory. So rapid evolution. We saw many examples of rapid evolution in previous studies, like the famous Darwin-Finch's trait dynamics, or interesting SNP frequency change with seasonal forcing in the genomic scale of Drosophila, or the combination of genotype and phenotype in Daphnia population in Oneida Lake of New York State, where specialists of cyanobacteria increase in late summer. And that can be driven by natural selection. So rapid evolution seems common in nature. And if you plot the speed of evolution versus the time period where a measurement was made, there's a clear negative relationship, which means that the direction of evolution is always changing. So if you look at the scale, if you look at the evolution in a very short time scale, then the speed can be very fast. But in the long time scale, it can be flattened by the canceling out of different direction of natural selection. And researchers found that this kind of rapid evolution is very important for population dynamics. For example, in chemostat systems with zooplankton and phytoplankton, if there's evolution in prey species, then the predator-prey cycles can be changed from the classical Rodogovoltera to cycles with longer phase and antiphase cycles. And this can also affect the extinction dynamics. If evolution is rapid enough, species may be able to avoid extinction by adapting to new environments rapidly, which is called evolution rescue. And also fishery in this evolution and that kind of stuff is very important for applied aspects of ecological science. But these studies basically focus on population dynamics. How does rapid evolution affect community dynamics? Well, there are several studies that examine the effects of rapid evolution on species coexistence. For example, some researchers use a theory for understanding how rapid evolution can stabilize, promote species coexistence via divergence of ecological traits or the fine-tuning with a trade-off between intraspecific and interspecific competition. And then there was a study showing how rapid evolution in duckweeds can change the competition dynamics. It's already 2 years ago. But for me, it's a little bit focusing on a limited topic, which is a trade-off between intraspecific and interspecific competition in stable environments. So I was wondering how rapid evolution can affect coexistence via sexual and social selection and in fluctuating environments. So I would like to start the first topic, which shows the density-dependent intraspecific adaptation load may promote species coexistence. So if you look at the textbook of behavioral ecology, you may realize that 9 chapters out of 15 are focusing on intraspecific interactions, like mating systems, sexualization, or cooperation. So if you want to synthesize ecology and evolutionary biology through the lens of eco-evolutionary dynamics, we should think of that kind of intraspecific interaction in addition to the trophic interactions. An interesting feature of this kind of intraspecific interactions is that there's a conflict between the conspecific individuals, and that can result in interesting patterns of evolutionary dynamics, as like the evolution of cheaters in ants, or evolution of dimorphism in females due to male mating harassment in damselflies, or polymorphism in birds. This is just like a hawk-dove game. And also extraordinary penis of bean beetles for the sexual conflict. So this can be seen as a kind of evolutionary tragedy of the commons, because in such conflict, selfish individuals can evolve to increase their own fitness at the expense of population growth. This is because it's basically a zero-sum or negative-sum game. There is a limited resource income to the population, and then they need to decide which proportion is allocated to intraspecific competition, and the rest of them goes to population growth. So we propose to call that reduction of the population growth as intraspecific adaptation load, as defined as like this. And there are several empirical evidence showing that this kind of adaptation load can be very large. So for example, in subsocial ants, some cheaters can evolve and invade the nest, and that can reduce the population growth rate for 25%. And in damselflies, the male mating harassment can reduce the population productivity around a half. And also there are many forms of this kind of intraspecific adaptation load, including production of male offspring that will not contribute to population growth, or male-male competition that can result in male mating harassment or infanticide, or female-male choice can also result in the reduction of population growth by the evolution of morphological or behavioral traits that can attract predators. Also, offspring competition for parental investment is just a load, does not contribute to growth. And one important feature of this kind of load is it can be density dependent. So if the conspecific density is very high, that high density can intensify the intraspecific conflict, and that can result in the density dependent selection of intraspecific load. So here are some examples from previous studies. X-axis is showing the population density, and the y-axis is showing the fitness of cheaters or proportion of males. Those are basically selfish traits, and that are increasing function of population densities. And this load can decrease the density, which means there should be a feedback between the population densities and that kind of selfish traits. So if we plot the population density versus selfish genotype frequency, higher population density should prefer the aversion of selfish traits, but lower population density should prefer the cooperative less selfish traits evolution. This is density-dependent selection. And then the black arrows indicate the intraspecific adaptation load. When the selfish genotypes are not so common in a population, then the population density can increase, but there are many selfish genotypes that can decrease. And this results in a cyclic feedback. And actually, there's a nice empirical study showing this kind of feedback by using yeast in experiments. So Sanchez et al. Showed that there's a feedback between the population density and the frequency of cooperative genotypes in a yeast population, and that can result in a cyclic dynamics. So here, y-axis is cooperative genotype frequency instead of selfish genotype frequency, and therefore the direction of calling is the opposite, but it's basically the same thing. The gray arrows indicate density-dependent selection, and the black arrows indicate intraspecific adaptation load. So this kind of population dynamics should affect community dynamics and species coexistence. But how can we understand it? We made a model for understanding this, and we tried to define individual fitness based on intraspecific competition for common resource. So here, W is the absolute fitness of an individual with a trait Z, and this defines the selfishness of the individual. And W is determined by the product of F and G. G is a common resource, and F is strength of intraspecific competition. So individuals can increase the strength of intraspecific competition by increasing Z, but that can result in the contribution to the common resource. And so G can be reduced by that selfishness. So if you think of fitness gradient of Z, the fitness gradient of F should be positive because individual can be increase its fitness by competing with conspecifics. But the partial derivative of Z is negative because increasing the selfishness should decrease the common resource. So this is a basic general framework, and we can think of specific examples based on this framework. For example, we can think of social dilemma of cooperating ants. And here, F is the individual fitness through intraspecific competition, and G is common resource through cooperation, like foraging or taking care of juveniles or that kind of stuff. And based on this fitness function, we can obtain the ESS trait value, which is an increasing function of the population size. So again, if the population density is very high, the selfish traits can evolve. And this can result in the reduction of the absolute fitness, which means the higher density result in the evolution of trait that reduces the population growth. And we put this evolution dynamics to this community dynamics. So here we consider the frequency of species I as P. And we consider replicator equations where the relative growth rate of each species determines the dynamics of frequencies. And here, Z is evolving along a fitness gradient with the speed of V. And if we assume a certain relationship between the frequency in a community P and the local population size N, as like this, then we can get these results. Here in the top right is showing the frequency-dependent thinness. When the frequency of species increase, the thinness decreases because of the intraspecific adaptation load. And because of this negative frequency dependence, all 5 species can coexist in the top right figure. And the bottom left figure shows the absolute thinness dynamics. And you can see that the common species tend to have lower thinness due to the intraspecific conflict. And the intraspecific adaptation load, which we defined previously, is showing us like this. And this again shows that the common species has higher intraspecific adaptation load. This is a second example of our general framework. And here we consider the classical Hamilton's sex allocation model, where mothers can produce male offspring with a proportion Z, and that Z determines the amount of contribution to the grandchildren generation. And so each mother can be selfish by producing more male offspring, but that can result in a common resource, in this case, females. And the well-known ESS is, again, density dependent, and dense population tend to have more male offsprings. And again, this results in negative frequency dependence, and 5 species can coexist due to the increased the feedback between the frequency and the selfishness. And actually, there was a study showing this kind of coexistence with sex allocation by using individual-based modeling as well. So as a conclusion for the first study, we asked how do intraspecific conflicts affect species coexistence? And then we answered higher density intensifies intraspecific conflicts, causing adaptation that can reduce population growth. And this is what we call density-dependent intraspecific adaptation load. And this results in negative density-dependent growth and stable coexistence. But this is just a theoretical framework and prediction, and we don't know how common it is in nature. And of course, there are several counterexamples where intraspecific conflicts can result in the extinction of competing species. For example, reproductive interference may be an outcome of intraspecific conflict as well. Also, sexual selection may improve the population level performance by effectively selecting the better mate, and that can result in competitive exclusion as well. And also, we haven't considered multi-level selection, where population level selection could be stronger than individual level selection. But that's also a different topic, and it may be interesting to think about the effects on long-term evolution for understanding this kind of species coexistence in longer timescales. Okay, that's all for the second topic. And I'll move on to the third topic, fluctuation-dependent coexistence. Here, I show that fluctuation-dependent coexistence with a competitively inferior species is possible via relative nonlinearity due to rapid evolution. So what is relative nonlinearity? One of the fluctuation-dependent coexistence mechanisms. It is just saying that coexistence is possible when competing species produces good environments for the other species. So if you plot the impact as x-axis and the response as y-axis, coexistence is possible when species 1 is stabilizing the fluctuations, but its response is rather fluctuation assisted. It prefers fluctuating environments, whereas the other species is better at destabilizing fluctuations. Sorry, better at producing fluctuations, but it prefers stable environments. And in this case, it results in negative frequency dependence in community dynamics, and two species can coexist via fluctuations. And this can be represented by a Zingi style figure, where x-axis is the mean value of the limiting factor, and the y-axis is the variance of the limiting factor. And if one species prefer stable environment, blue species zero growth ice line should be something like this. And if the orange species is neutral in terms of the fluctuation, it should be vertical. And if these two species have different impacts on fluctuations, their impact vector should be something like this. The blue species is destabilizing, increasing the variance. And the orange species is stabilizing, decreasing the variance. And this can result in coexistence. And a similar version of this figure without these impact vectors shown in Chase and Lebold in 2003. And this is a most famous example of coexistence via fluctuations, originally from Armstrong and McGehee, where species 1 has a lower resource requirement and species 2 has a higher growth rate. And this can result in coexistence as like this. So you can see that species 2 is increasing when the system is fluctuating, whereas species 1 is increasing when the system is relatively stable. But because of that increase, the species produces good environments for the competing species, and that results in the negative frequency dependence. And this type of coexistence is sometimes called the greener opportunist trade-off, because species 1 with lower R star is called greener, and the orange species with higher growth rate is called opportunist, according to Grover's 1990 paper. So when I understand this mechanism, I was wondering how rapid evolution can promote this type of coexistence. And based on some mathematical models by Michael Cortes and Swati Patel, we knew that rapidly evolving species can stabilize population fluctuations. It is also possible for rapidly evolving species to destabilize, produces population cycles, but depending on the trade-off or parameter values, it can stabilize fluctuations. And also rapidly evolving species should prefer fluctuating environments because it should have some Thinness benefit by rapidly evolving to fluctuating, rapidly changing environments. So I thought that this orange species can be rapidly evolving species, and that may broaden the parameter space that enable this type of coexistence. So I made this very simple model where prey species are growing according to the logistic growth. And then there are two consumers with holding type 2 functional response. And also we assume a trade-off between the attack rate and the mortality rate as like this. And again, the trait is evolving according to the Thinness gradient. So when the resource is abundant, it is better for consumer to invest the trait to have more higher attack rate. But when resource is scarce, it should be better to have a higher attack rate with lower mortality rate. So this kind of adaptive foraging is actually very similar to breeding suppression a kind of plasticity where organisms are actively forage in better environments and stop foraging for reducing the mortality rate in worse environments. So basically, we are talking about rapid evolution, but the same mechanism should work in phenotypically plastic traits as well. And then we found that rapid evolution can broaden the parameter space for coexistence. So the top right figure shows the functional response, the per capita growth rate of non-evolving species 1 and the evolving species 2. And the gray lines are showing the per capita growth rate of species 2 with a certain trait value. And when species 2 does not evolve, it is very difficult for this species to coexist with species 1. But with evolution, this can produce the green opportunity trade-off, and it's very easy for them to coexist. And the resultant trajectories of the per capita growth rate looks like this. And the top right figure shows the actual time series of numerical simulations of coexisting two species. And the bottom right figure shows the phase diagram where x-axis is adaptation variance of the trait, and the y-axis is some parameter of species 2. So you can see that when v is 0, the parameter space for coexistence is very limited. And this is the classical green opportunity trade-off coexistence. But if you increase the variance, that promotes rapid evolution, and that can result in coexistence of the two species. We also found that coexistence is also possible without the green opportunity trade-off. So the top left figure shows the per capita growth rate of species 1 and 2. And you can see that species 1 is a greener because it has a lower resource requirement, a lower R star. But species 1 is also an opportunist because it has a higher growth rate. So it seems very difficult for species 2 to coexist with species 1. But if you look at this carefully, when the resource is very scarce, species 2 has a higher growth rate than species 1. And this results in coexistence when species 2 is evolving, as like the top right figure, where again, you can see that the non-evolving species 1 is increasing when the system is relatively stable, but the evolving species 2 is increasing when the system is largely fluctuating. And again, the phase diagram is showing the effects of adaptation variance on the parameter conditions for coexistence. But in this case, when V is 0, there is no coexistence region, which means it is impossible for the two species to coexist without rapid evolution in this case, because there is no green opportunity trade-off. So as a conclusion of this study, we show that the evolving species stabilize population fluctuations, and this results in the increase of the non-evolving species. And the non-evolving species produces fluctuations, and this is good for the evolving species, and that results in coexistence via fluctuations. And recent empirical studies have shown that actually fluctuation-dependent coexistence mechanism may be more important than previously envisaged. So our study that showed the potential effects of rapid evolution for broadening the parameter space for fluctuation-dependent coexistence is supporting this kind of view, which means that fluctuation dependence is everywhere and important for coexistence. Okay, so that's the second topic. And I was talking about coexistence theory and eco-evolutionary dynamics through my talk, but you may realize that they have some common currency and some similarities. Both of them are very interested in fluctuating environments, and both of them are interested in diversity. Coexistence theory is about the maintenance of species diversity, and eco-evolutionary dynamics always need some genetic diversity for evolution to occur. Also, they considered the partitioning of various factors contributing to certain dynamics. So Chesson's coexistence theory or expanded modern coexistence theory basically consider the contribution of different factors to the coexistence as like this, bottom left figure. And also theories on eco-evolutionary dynamics has considered the contribution of rapid evolution and contemporary ecological dynamics and plasticity on eco-evolutionary dynamics. So this kind of methodology may be used, and it may be possible to synthesize these two disciplines for better understanding the rapidly evolving, adapting nature. And that's all for my talk. Thank you very much.
Thank you so much, Masato. Now, if anybody has a question, then please raise your hand in the participant list and I will be calling on you. Any questions? Well, while people are thinking, I can ask a question. Let's see. Well, one thing is, if you show, sorry, you just took down the slides. Can you please put them up again?
Okay.
But actually, Jonathan is asking a question in the meantime, so let's listen to him first.
That's very kind of you, Gary. But I'm happy to have your question go first. So why don't you give it?
Okay, thanks. Okay. So in that case, if you go to those phase plots about coexistence in the last part of the talk.
Okay.
I'll let you know. Yes.
Yep.
More there. Is the fact that the coexistence region for a given level of an additive genetic variance is not what's the word? Not compact. Is that interesting, or is that just an artifact of the parameter on the y-axis? So that such that for certain values of the additive genetic variance, you can coexist for low or high values of B2, but not in between.
Mm-hmm. Mm-hmm. I'm not sure. Probably the trade-off between the attack rate and mortality may be affecting these results as well.
Okay.
Yeah.
Okay, thanks. And just one small thing I wanted to make sure of is when you do the replicator equation and track the frequencies, is the total population size forced? You have like on those plots exactly that you were showing, those line graphs. Are the total community size forced to be constant, or is that?
Yes, exactly.
Yes, it is. Okay.
Yeah. So I think this kind of frequency dynamics cannot be applied to the situation where the community size is increasing or decreasing.
Okay.
Yeah, we are just assuming that the total community size is stable, and only the frequency of different species are changing.
Okay. And the model structure is such that it allows for that.
Yes, it's just replicator dynamics. So.
Oh yeah, I guess I'm not phrasing it very well. So the replicator dynamics, as is written on this slide, could be formulated for any sort of model, right? And it's just that maybe the total population size is also increasing or decreasing. But what you said that you kept that fixed. And is there some mechanism in the model that makes sure that it's kept fixed?
No, I think that's just our assumption that energy income to the community is fixed, and therefore only the frequencies are changing in a community.
Okay, thanks. All right, then, Jonathan, please go ahead.
Yeah, thanks for the talk, Masato. That was great. And thanks, Gary, for helping organize. Can you go back to the slide that Gary had you on a minute ago, the phase plane?
Yep.
So I think, like Gary, I was looking at this, and there's obviously some interesting shapes here that are worth commenting on. But I was struck by two things. Obviously, there's this particular threshold on the x-axis variable which I guess was, sorry, I'm not seeing the full bottom. Anyway, but yeah, it was the trait variation, right? Yeah, that adaptation variation. That you reach some sort of threshold, and then suddenly the ecological region expands massively. And I'm imagining you have this family of curves for species 2's trait possibilities, following from species trait possibilities. Is this basically the point at which you suddenly now, I don't know, allow these curves to generate what would be sort of nonlinearity in a non-evolving system? I guess I'm trying to ask is, can you, I mean, Masato and I have talked about this a little bit already, but can you look at sort of like sort of an invasion condition type scenario and identify essentially where this point would be, because you now capture a curve which will allow you to sort of meet the conditions of even ecological coexistence, even without the evolutionary dynamics coupled to the ecological questions? I don't know if my question makes sense, but I'm trying to understand, first of all, why there's that discontinuity, and then could that be predicted from knowledge of the invasion condition?
Yeah, I haven't thought of that invasion condition for this study. But yeah, that's interesting, because, you know, invasion growth rate is a kind of currency of Jason's coexistence theory, right? So
yeah, okay, it's fine. But what is going on there? Even just forget my detailed hypothesis. Why at around 0.03 adaptation variation do you suddenly expand the coexistence region massively?
Yeah, it's interesting. I will check it in detail.
Okay. You're muted, Gary.
I cannot hear you, Gary.
You're muted.
Apologies for that. So I was saying thank you, and Chris, please go ahead.
All right, so great talk. Question about the first part with the intraspecific adaptation load. What can you say about the diversity of species that can coexist by that mechanism, or like maybe the relative abundance of species that coexist by that mechanism, and maybe how it depends on productivity? It seems like, you know, maybe you can like come up with some rule of thumb, or don't know.
Sorry, could you say the question again?
Yeah, so, you know, when you have the coexistence by the intraspecific adaptation load, can you say anything about, for example, the number of species that could coexist by that mechanism, how it depends on ecosystem productivity, and maybe something about the relative abundance of species that coexist? Because I noticed, you know, despite, you know, the coexistence, you had like, you know, some were relative winners, some were relative losers. So I'm just wondering if there's anything you can say more about community structure when you have coexistence by that mechanism.
Yes, actually, these differences in different species are arising from our parameter settings. So we just change the basic parameters, like the basic productivity of lambda, the different numbers of lambda for different species. And that's why we have different dynamics. Otherwise, they are all equivalent. So basically, any number of species can coexist in this framework. And actually, Kobayashi's paper examined that kind of question. And he found that many numbers of species can coexist, and they show some sort of what is called species abundance curve based on his parameterization. So I don't know how that parameterization affects the community structure in his paper, but it may be interesting to work on that.
All right, thanks. Yeah, I'll check out those papers for details.
Thanks.
Thank you so much. Martin, please go ahead.
Hi, Masato. Great talk.
Okay.
So for your second part, you're assuming that genetic variance is constant. Do you think the fluctuation dependent rapid evolution impacts on coexistence would be less likely to help coexistence if variance decline with population size?
Yes, I think so. And especially you can see that the population densities are very low in these fluctuations. I think in reality, it may be a little bit difficult for evolving species to have an evolution potential when their abundance is very low. And so, yeah, I think it may be interesting to work on the individual-based models or stochastic simulations for understanding how low densities can affect the evolvability and the likelihood of coexistence. And it depends on the amplitudes of cycles as well.
Right. And are you exploring coevolution in this model as well at some point?
Not yet.
Okay.
Yeah, but I think if one species is evolving rapidly and the other species are evolving very slowly, then the same type of mechanism should work even in coevolution scenario.
Right.
Yep.
Cool. Thank you.
Thanks.
Thank you very much. Are there any other questions? Yes, Andre, please go ahead.
Thanks, Masato, for a very interesting talk. I actually, this is maybe a little bit of follow-up on what Jonathan asked. It's about this border between coexistence and species two only that you see in the bottom right graph. Is it possible that it has to do with a switch between that the impact of a species is more due to either a numerical response in the density versus a response in the individual trait? Because you know, the impact of the species as a whole is, of course, a product of its numerical density and its individual level trait. And you scale the dynamics of the trait with the rate of species, with the change in species, the density. And so is there a switch point where actually you can determine that the change in the impact on the resource is either due to a change in N or a change in X?
Yeah, I think that's an interesting question. And probably we can use a partitioning method of eco-evolutionary dynamics, the Giba method, for understanding the relative contribution of traits and densities. And it's basically dynamics mediated by resource densities.
Yeah. So you have to look at the decomposition of the foraging rate, the thing behind the sigma, the summation sign.
Yes. Yep. Exactly. Thanks.
Thank you very much. Martin, go ahead.
All right, just think a bit more about Jonathan's question of why you have that change in coexistence at 0.03. Do you think that has to do with that you need a pretty large genetic variance to be able to sample a lot of the nonlinearity in the attack rate and mortality trade-off. Does that make sense?
Yeah, I think, yeah, probably this threshold response is showing the needed amount of genetic variation for stabilizing populations
Sure.
densities. Yeah, so that's similar to some sort of bifurcation plot, where if you increase the amount of genetic variation, then the population cycles are decreased, and then at some point it's stabilized. And there's some sort of threshold where population cycles are small enough for the this kind of coexistence mechanism can
Right.
work very well. Yeah.
But do you feel like if you had a stronger nonlinearity, you would need less genetic variance to expand the coexistence area?
Nonlinearity in the per capita growth rate?
This is where I'm not an expert to speak about this. Yeah, or the nonlinear in your trade-off, right? Between mortality and attack rate, which will affect growth rate.
Yeah,
if I'm saying that
yeah.
correctly.
Could be, yeah, because the nonlinearity can affect the likelihood of stabilization. So, yes, I think that should be very influential for determining these dynamics.
Okay, thank you. Andre, go ahead.
Yeah, one last question about this model. You don't do anything to actually bound the X value to the positive domain, as far as I can see. So
yes.
Is there a possibility that your X actually goes negative?
Well, actually, in our model and parameter setting, there's a stabilizing selection to intermediate trait value. And that's why the trait dynamics does not need to be bounded by the artificial V value. And yeah, so it does not go to the negative values.
Thanks.
Okay, are there any other questions? While people are thinking whether they have a question,
sorry,
I might.
Georgi,
yes. Of course,
yes,
go ahead.
Thank you,
yes,
Masato. Great talk. I have a question that follows on this fixed genetic, how do you say, sorry, that, yes.
Variance.
Yes, the variance, because yes, it's an interesting question if you did this with an individual-based model, how the amount of genetic variance would vary, and could there be a threshold in the accumulation of the genetic variance at some point in the system, so that it's not only a threshold in terms of how wide the coexistence is, but what would happen to sustaining or eventually even in an evolutionary model to the amount of the genetic variance, so that could the dynamics itself, sort of take you, depending on conditions, across a threshold in your ability to expand the genetic variance. Because in the very fluctuating dynamics where you would lose, you would lose some of it, and in the more stable dynamics, you could perhaps expand it. I don't know. I think that's an interesting point.
Yeah, I think so.
In comparison to the constant case here.
Yeah, I think in individual-based models, the genetic variance is not constant parameter, but it's a variable dynamically changing according to population densities, right? And then we need to think about the maintenance of genetic variation for rapid evolution to occur. and the maintenance of species diversity for understanding species coexistence simultaneously.
Yes, but
So
I think
that
it could be intertwined, right? So in a way that it's
Yes.
not just the maintenance, but the expansion of the genetic variants that you have available for this
Yes.
kind of evolution.
Yep. And fluctuating selection can expand the parameter space for the genetic variation as like the storage effect or other type of mechanism. So yeah, I think that's interesting to think about the mutation selection balance and the effects of stochasticity and the roles of population cycles on the genetic diversity dynamics.
Yeah, thank you.
Thanks.
Thank you very much. Are there any other questions? While people are thinking, I might have one small question, one technical question. When towards the beginning of the talk, when you were talking about the cheaters, the fitness function was assumed to have a specific form. Exactly. Is that an assumption, or can you always write the fitness this way, or is there some sort of class of situations in which this is possible?
So this is a kind of inclusive theoretical framework for understanding the intraspecific conflict or intraspecific competition. So we try to represent the intraspecific competition by this term, F times G, and then H terms can be needed when you think about the sex allocation. But this H is not needed for the case of social dilemma. So this is a kind of general framework, but not universal framework.
No, it makes sense because your model that you have like a slide on or two slides on fits into this nicely, right? That one. So presumably there will be many models which fulfill this, but it's not necessary. So it's not like every model must, by construction, somehow fulfill this.
Yeah, exactly.
Okay. That's good to know. Okay, thanks so much. Finally, any other more questions? Well, if there are no more questions, then thank you again so much, Masato, for the talk, and especially for hanging in there so late at night, your place.
Thank you.
And thank you everybody for coming. Our next seminar is going to be on May 18th, and it's going to be Cinzia Sorrenzina presenting at the time. So mark that in your calendars. A reminder will be coming. Thank you again so much for coming, and we will see you soon. Bye, everyone.